Let's do page 65, factorial.pi. This is quadratic.pi from a few pages earlier. Now we're at chapter 3.3, accumulating results, factorial. So let's do it. We're in Atom. Let's do the new file. Factorial.pi. Save it. Factorial.pi. And then program compute factorial of a number. We want to be thinking how we're going to solve it even before we look at it, right? So the factorial is like 6 with an exclamation point or an exclamation mark. It's basically 6 times every integer all the way down to 1 at a time. So 6 times 5 times 4 times 3 times 2 times 1. Pretty straightforward, right? You can probably do it without looking. Illustrates the for loop with an accumulator. And then, okay. Let's check it out. Let's do eval input. Please enter a whole number. So this is going to probably be like n minus 1, right? For n in range 6, and we're going to step, it's going to be -1, right? So it's going to be, well, I don't want to, you guys probably won't believe it about looking, but it's okay. All right, we'll just go, because I just glanced and like, okay, so we'll just go over it. But yeah, that's just what I'm thinking. Because it's start, stop, step, right? So our step's going to be -1 because we're going to go down 1. So let's just go over it. So fact equals 1. Factor in range. So now the range is going to be n, and then it's going to be stop. We're going to stop at 0, right? Because it's going to go to 1. So we're going to go to 1 below 1. We're going to go 1 past the number that we want to hit. However, multiplying by 1, we don't need to multiply by 1. We need to multiply by 2, and then we can stop, because anything times 1 is itself. So we don't even need to go to 0. We can just stop at 1. So this will give us the same answer as this. But let's just do that, because that's what the book says. And then -1, right? Because we're going down 1. So this is a descending range. And then we're going to indent here. So as part of our for loop, fact is equals fact times factor. And this is outside the loop. So once that loop is done, then fact has been totally updated after it goes through range of n all the way down to 1, stepping down -1 the whole way. The factorial of comma n is, and then fact, right? So that's going to be outside of the loop. It's going to be at the end. Once the loop is already updated fact, where the loop is completed its run, that's why we don't indent that in. So that's outside of the loop. Well, let's just see what we would do. So if we zoomed it in here, what do you think would happen? Yes, it would update. It would update every single one. So let's do it there. Let's do it there right now. Let's just check it out. That's one thing I heard from some of these profs, especially, you know, even the first prof that I took at this Chemeketa college. It was a C++ class. Andrew Scholar, I might have mentioned it before. He's fantastic. We went to the same college actually, but he studied like cognitive science, so much harder um, studies. I was doing, you know, English, so you know it's a little bit easier, especially if you know how to write. You know, it's just a lot easier when you're doing like really hard, you know, science and math and physics and computer science and engineer. You know, it's just a lot more meaty. So I definitely give him a lot of kudos. But he was solid. He kept saying like try different stuff, and everywhere I go, when I talk to people that have been in the industry for a long time, I've been working on Launch Code. It's like this free sort of it's a nonprofit that was started by um, I believe the gentleman that started Twitter. I think it was, well, Jim McKelvey, I believe. I'm not sure if Jack Dorsey is involved as well, but it might have been both of those guys. Anyways, it's it's in the city where I'm at now, and um, in Portland, and you know, and the gentleman there named Al, he's running the program there in the class, and he always says that just keep trying different stuff, keep poking around, keep, you know, and all the helpers, all the class assistant, they're called TFs. They all say the same thing too. So it's really great to hear. You know, there's the community at large in general is very supportive, and they always, you know, they always give you like, they almost always give you really solid advice, especially when it comes to learning and memorizing. And so, you know, writing things out longhand. Al's a huge fan of that. I totally agree. Coming from tutoring and doing research on learning modalities and memory and whatnot, yeah, like writing things down tangibly, you know, it tends to stick more. So I love that he's talking about that. And also, yeah, but just trying different stuff. So let's just try different stuff. So if we go to, this is an earlier program that if you guys recognize this. Okay, so let's go to open. This is going to be factorial. Let's open it up. So let's see. Oh, it didn't save it. Okay, so coming up here, I want to make sure that I save it. So I guess I didn't save it. Okay, so then go back here, open. All right, let's check it out. Looks pretty good. This time we put main and not math like I did last time. Okay, let's run it. Now remember, this is going to update us every time we go through the loop, right? So which is kind of cool because then it's sort of a running tab. So let's do 6. There it is. So it, I mean, it's written wrong in terms of factorial of 6, factorial of 6, factorial of 6. We could have changed it, you know, to make it more legible, easier to understand and whatnot. But you're seeing what's happening, right? So it's just 6 is the fact. Now it's 6 times 5, which is 30. 30 is our new fact. Now it's 30 times 4. 30 times 4. So 30 is the fact. 4 is the factor, right? Because we're iterating through this list called factor. So it's just going to be 2, 3, 4. So then, you know, and then 360 and 720. So that's what it's doing. But if we pull it out, it's still part of our function. So it's indented, but it's not part of our loop anymore. It's outside the loop. That's what's so great about Python is you don't, you know, there's, you know, as long as you're using the same number of spaces, it knows if it's inside of a loop or inside of a function or outside of a function or outside of a loop or both, etc. So this is inside of the function, but outside of the loop because it's indented in the function definition or declaration, and but it's not indented in the for loop. So it's going to be, so after this runs, then it's going to print this. Okay, here we go. So let's save it and let's run it. Let's enter the same whole number, 720. There it is. So it gives us the final tally. All right, so that was page 65, 3.3, accumulating results, factorial. Now we're at 3.4, limitations of computer arithmetic. So please enter a whole number, and then we enter 100, and it's a really, really long number. So we could try it. Let's try running it again. Let's see it. Just for practice. Practice is a long number, and then all those zeros at the end. Which is really the same thing that the book got on page 66 here. So recent versions of Python have no difficulty with calculation, although recent versions, older versions of Python would not fare as well. And then they've got Java, go over some examples with Java. Professor Zelle goes through on page 67, the bits, 3 bits. 3 bits allows us to represent 8 different values by adding a 0 or 1 to each of the 4 2-bit patterns. So it goes over bits, 2 over 32, 2 to the 32nd over 2 equals 2 to the 31. So that's why the range of integers that can be represented in a 32-bit int value is -2 to the 31st power to 2 to the 31st power minus 1. So let's do let's go to some more of this IDLE. Now, obviously, you want to read this, really know it. Index cards, get this down cold. I really like this book. I really like how clear it is, the examples and all of that. And yeah, I like to just write examples, just even the simple examples. So the integer of 4.5, again, I might have mentioned this in previous videos. You might have already known this, but it's going to go to the lowest number. So if it's int -4.5, it's actually going to go to -5. Well, actually, let's just do -4.1, because you think it's going to go to -4, but it's not. It actually goes to -5. It goes to the lowest. Oh, excuse me. This is a little bit different. So integer of -4.1 is -4. There is a number that goes to -5. I think we went over it before. And again, this is why I'm doing this now, because this is how I learn. If I forget something, then I want to go over it again with you guys and make sure that I catch it. So the int of -4.1 is -4. Let's do the int of -4.5. -4. Let's do the int of -4.9. -4. So -4.9 is close to -5. But the int version actually gets closer to 0. Interesting. Interesting. Oh, I'm thinking about the division sign. So if you do like 1 divided by 4, it's going to be 0.25. But if you do 1 /4, it goes to 0. Now, if you do -1/4, it's -0.25. If I do -1/4, it's going to be -1. Exactly. Okay, so here's the distinction. So if you're trying to do int, if you're trying to, it's basically a function. If you're trying to perform the int function, which makes whatever's inside the parameter the argument. So whatever the argument is of the int function, that gets changed. So the int of 4.5 is going to be 4. So it's actually going to get less negative. So it's going to go more right. Right? So when you use the int function, or when you call the int function, I don't know if I'm using the right terminology, because I don't know if you're actually calling it, because you're not really defining it. But basically, when you perform the int function, it goes more to the right on the number line. So that's why int 4.5 goes to 4. That's why int negative 4.1 goes to negative 4. And then these other ints, negative 4.5 goes to negative 4, negative 4.9 goes to negative 4. So even though it should round up to negative, or round down rather, to negative 5, it's actually rounding up to negative 4, to the nearest number that's to the right, nearest whole number that's to the right. So it just truncates this number here, essentially. That's all it does. The int just cuts this off. That's really the easiest way that I would analyze this. Cuts this off. And the math majors can help me out with this. So it just would cut that, cut that, cut that. I watched a speech by Mark Zuckerberg, and he was talking. And it was funny because the class wasn't that full, but I'm sure now it's like standing room only. But it was still a growing company back then. But it was he came to talk at like CS50. It's on YouTube. But he was talking about how, you know, math majors can pick this stuff up fast. And if you already know a language like extremely well, like C or something like that, maybe even Python, that, you know, learning new languages, you can really pick it up fast. And he's also was talking about, you know, it can sound a little bit elitist, but I mean, maybe it's true. I mean, they you know, I tend to agree with some of the stuff he was saying about, you know, if you're younger, you can learn more. That's probably true. Your brain is just more elastic. But I think a lot of it too depends on someone's brain. If someone's been really working diligently, you know, and that's kind of what he was hinting at as well. Is like if these guys have been working really, really hard their whole lives, and then they want to go work at Facebook or these companies, like they're generally gonna pick stuff up faster and whatnot. So it's really, you know, I also think that if someone's a lifelong learner, you know, that they're generally, their brain's going to be a little bit more elastic than if you're, you know, than if you don't really actively learn aggressively and heavily and in a rigorous manner over the years. So, but yeah, I thought it was kind of interesting. But yeah, so maybe the math guys can help me out on this. But it looks like we're just basically truncating this suffix here. And that's an easy way to explain it, to remember it as well for int. And then for the integer division, this double cut here, it goes actually to the far left on the number line. So it's the whole number that is either less positive. It's the whole number that is more on the left of that. So let's do a few more of these just as an example. Let's do int 3.9. See, so it just cuts that 0.9, and then float 4, and then float. So yeah, so float 4 makes it float 4.5. Float 4.5 makes it 4.5. It doesn't round it at all. It just gives you the decimal. It's a float, right? It gives you a decimal. So if you're given a decimal, then it just re-returns or re-enters the same decimal. So int 3.3. So yeah, so that makes sense, right? That's an int. Our ints just get cut. Literally, it's truncated. So you integerize. And then int float 3.3. Let's see what that is. All right, well, let's see what it is. So just remembering from math, our float 3.3 is going to be 3.3. And then our int of 3.3 is going to be 3. So I think it's going to be 3. Yep, okay. So now int float of 3. Now let's check this out. So the float of 3 is 3.0. The int of 3.0 is 3. So it's 3. Yes. Okay. All right, so now we're going to round 3.143. And rounding 3.5 is probably going to be 4, which is standard in regular math. Let's see if it works in Python. Yes. So that's not too bad. So now we're going to import math. And now we're going to do the problems on page 70 and 71. So we're going to do math.py. There it is. Now we're going to round it. So let's round math.pi. And it's going to be comma 2. So that's going to be to 2 places. Here's where we're learning about money. Here's where we're learning about rounding. Here's where we're learning about helping the user out. If we have some answer that's 19, decimal places long, it's been a little bit of an encumbrance, just visually sort of obnoxious. This could help us. Boom, there it is. It's that rounding. So we round, and then there's the number, whatever the variable is, or the number, which would be obviously potentially be like a decimal number with a lot of decimal places, and then just put comma 2. There it is. We just solved that, so we won't have that problem from now on. Hopefully. I mean, we want to get more and more exposure, obviously, just to keep practicing. But so now we're on page 71. Let's do round math.pi 3. Now, what do we think that's going to do? It's the other thing I like to do too is just like try to guess. So I'm guessing it's going to be 3 places to the thousandths place. It is, right? Tenths, hundredths, thousandths. And Khan Academy is really helpful. There are a lot of sites that are really helpful as far as like math, really strengthening your math. You don't have to be like this math genius, but it definitely helps for programming, especially some of this back-end stuff, or like just the core of programming and problem solving and whatnot. It's just, it can't hurt. Although I have heard some people say that people with my background can do well, and that there are potential not only work opportunities, but just just in terms of thinking, in terms of picking stuff up, and in terms of being able to communicate about these problems and about these issues that I tend to think a wide variety of backgrounds can be very helpful in these technical roles. But it is, I'm sure there are huge benefits to having a mathy background, and then there are probably some benefits also to having more of a humanities or liberal arts background. It just depends, but yeah, it's definitely something that I find interesting. Okay, so we're gonna round it 2, and then we're gonna print it. Okay, well that's probably the same as this, only we're printing it, right? It's probably pretty similar. It's just trying to show us the syntax. Yeah, there it is, 3.14. Okay, cool. All right, then the last one. Math.pi, so we're applying the pi method to the math module, and that's going to be 3. That makes sense, right? It's going to be 3.142, yeah. So yeah, that's 71. Chapter summary, check it out. 71, 72. Ints and floats, int data type. It's talking about explicitly converting one data type into another using the functions float, int, and round. Then the other exercises and questions we're going to go over as well. And we're going to do the programming exercises as well on page 76. All right, thanks a lot.